Okay, so uh, last week I got you guys to watch the beginning of the probability chapter. We'll do a brief review there. And I posted on Moodle just now, though. I posted a formula sheet because we're online, and I've only taught this course online. I don't have a specific formula sheet, but I'm basing it off of an old one. And so it's just something for you to go off of. But of course, you're working open book, so you can, have whatever formulas you want. So this is just kind of a jumping off point if you want to have this one and kind of write around it. But it looks like this. It's for Stat 121 and 124, which is basically the same course, except we go a little bit deeper into each of the topics for later on. But that's it. So it's pretty well the same course. So it's a little bit confusing because it's broken up by the old chapter numbers. So chapter 2 is probability. Now chapter 3 is probability. But it's just some formulas to get you started. Okay. Okay. Where did oh yeah, I asked you to watch the first 50 minutes, which doesn't quite finish section 3.1. So I want to get into that. But for some review, and I always feel like I'm forgetting something administrative, but I guess we'll see if anything pops up. Oh yeah, I'll bump it down. So quiz number 1 will open on Friday. Oh, now it says you've turned on the live transcript. I already did that. Weird. Okay. Quiz number 1 will open on Friday. And close. I can't remember if we talked about it last day, but anyways, and close Sunday night. Let me go back and see if we talked about it last week.
We did.
Yeah. We did, right? Yeah, I'm having this like deja vu. I'm looking at you across the room. And we talked about it, right?
Yes. Yes.
Then that's all I'll say about it. Thank you. Otherwise, I would have been blabbing about the quiz again. Okay, so for some quick review, right, we're talking about the probability section. So probability, we're going to be talking about probability a lot, but this is the only section that I call probability, and it's going to feel kind of discombobulated because later on we're going to talk about probabilities in a slightly different way, but here we just kind of lay the ground rules for what probability is. So probability is a percentage or a proportion. So it is a proportion. I know I mentioned this last day, but it's so important. And it's approximately a percentage, right? We have to multiply by 100 to get a percentage, but besides that, they're all the same, right? So notice all these 3 P's, we use them interchangeably. So that means that a question might ask, what is the probability of this happening? Or what proportion of times does this happen? Or what percentage of times does this happen? But those questions are all the same. Okay. So some properties of probabilities that we have to always kind of keep in mind are that a probability, and we use this probability notation, P of A, so the probability of some outcome A or some event A happening. So A is just a placeholder for something that can happen, has to be between 0 and 1. 0 and 1. Okay. So what this says is the probability, or any probability must be between 0 and 1. Okay. And then we said the probability of the entire sample space, which is all possible outcomes, and maybe I'll just bump this over here. So we can keep it nice and tight here. Totally cheating with my writing here. Okay, so the probability of S has to equal 1. So where S is all possible outcomes. So the total probability of all possible outcomes must be 1. Right? If we consider all possible outcomes, so S is the sample space. S is the sample space, which is all possible outcomes. For example, if I roll a die, then the possible outcomes, we're assuming a standard 6-sided die, the possible outcomes are 1, 2, 3, 4, 5, 6. And those are all possible outcomes. So if I say, okay, well, what's the probability of one of those things happening if I roll a die? Well, it should be 1, right? Because one of those things will always happen, right? And so you've considered all possible outcomes. These properties are actually outlined on that formula sheet. So let me grab it here, the chunk that we're looking at today. So here, P of A is between 0 and 1. That's a standard property, and the probability of S is 1. We also talked about the complement of an event. Kind of fun to say. Okay. So the complement of A is everything that's not in A. So everything in the sample space, but not in A. Okay, so it's the complement of A. So it's everything that's not A. So you can read this as kind of not A. Sometimes I'll slip up and I might use like a prime, which is also the complement. So there's different notation that we could use for the complement, but it should be obvious from the context. So if we have the probability of the complement of A, so if A is the event of rolling a 2 and a 3, then the complement of A would be a 1, a 4, a 5, or a 6, right? So let's say that, for example, if A is the event, and we use set notation of rolling a 2 or a 3, then the complement of A is everything that's not 2 or 3. So 1, 4, 5, 6. Those events, we can attach probabilities to those. And so kind of obvious, right? If I say, okay, each of these outcomes have the same probability, in this case, we assume just a fair 6-sided die, then the probability of A would be 2 out of 6, right? Or 1/3. And then the probability of not getting A would be 4 out of 6, right? Which we saw kind of before too, when I talked about pie charts, for example, especially if we have kind of yes, no situation, then if I know the proportion of yeses, then I also know the proportion of nos if there are only 2 possible outcomes, right? So either you're in A or you're not in A, and it's the same situation. And then we developed the idea of this general addition rule. Okay, and so we said that, okay, the general addition rule says that if we want to find the probability of A or B in general, right, it's going to be the probability of A, plus the probability of B minus the probability of A and B. I think the easiest way to kind of summarize this general addition rule is with a Venn diagram, right? And so if we have a Venn diagram that looks like this, right, I have some outcome A and some outcome B. Okay. Each circle shows the events that are in A and B, but also we could talk about them as probabilities, right? And so this square outside is the entire sample space. So usually we put this rectangle around here to signify that this is the sample space. Those are all the possible things that can happen. And not all things have to be in A or B. They can be outside A and B, and that's okay, right? But we also need to show that there's some overlap here, right? There's a possibility for joint outcomes in A or B. So if we go back to the die, for example, right, then if A and B, or if A is, let's keep it as 2, 3, right? Then if B is 3, 4, then there's overlap there. Then both the events happen if 3 happens, right? And so we have this overlap here, and this overlap is the probability, or this is A and B. And now I'm drawing a blank, but I can't remember if we said, if I use this notation, A and B, so A intersect B, can't remember. Anyways, usually we use this little intersection or a cap. So this is the intersection, which is and, versus the union, which is or. And maybe I'll bump this out here. Versus the U, which is the union. So you can have and or. So the intersection or the union. I can't remember if I introduced that in the video or not, but probably, but maybe not. But that's just some shorthand. Typically, because we spend so little time in this section, I'll probably just use the words anyways, and or, but sometimes it's nice if you're able to recognize the shorthand, the set notation. Okay, so if we think about this overlap here, A and B, then if the area of the circle A is the probability, and the area of circle B is its probability, then we're counting this overlap twice, right? So basically what happens, if I want to know A or B is everything in A or B, right? So this A or B is just everything in A or B. But you want to make sure that you don't count the overlap twice. So for that reason, it's the probability of A, so it's the A circle, plus the probability of B, but notice we've counted that overlap twice now. So then I have to subtract that overlap once, and then I'm back on track. And then I'm able to find the probability of A or B. So usually we have to be kind of flexible with finding these probabilities. So as long as you have 3 out of these 4 components, you can find the 4th one, right? You might need to rearrange a little bit, but usually I'll be kind of sneaky and I'll ask you to find the probability of A and B, for example, but I'll give you the probability of A or B, the probability of A and the probability of B, or you'll have found them kind of throughout the problem, and then I'll ask you to find a different component, right? But here, given 3 of the 4 pieces of information, we can solve for the 4th. Okay, so that's just something to keep in mind. Okay, so that's kind of up to here on the formula sheet, the probability of A or B. We didn't talk about independent events, so that's kind of where I want to pick up. Unless you kept watching, then good for you. But I only said the first 15 minutes, so I'll assume you haven't. Okay, so independent events. Independent events or independent probabilities are when knowing the outcome of one doesn't affect the probability of the next outcome. So a lot of the time we don't have independent events, but for things like if you roll a die, then it doesn't matter if you have had 6 ones in a row. The next one has the same, so the next roll has the exact same probability of rolling a 1, right? So those would be independent events. Whereas if you have a deck of cards and you know that 3, so you're holding 3 red cards, then you also know that the probability of having another red card is slightly lower, right? Because you already have 3 of those red cards, meaning that there would be more black cards in the deck. Right, assuming that you're the only player, that rarely happens, right? But it does give you some insight, right? So then those would be non-independent events. And for some reason, we don't really call them dependent events. We just call them non-independent events. I don't know why. You can call them dependent events. People will understand, but for some reason we don't. And it's weird. Oh yeah, let me just, oh yeah, and we talked about expected values, but I'll leave that. We'll come back to that in 3.4, I think. Okay. Independent events. Let's go bring that in here. It's like, why did I write it out if it's here all nice? Oh well. So 2 events or outcomes, and don't be kind of caught up in the events versus outcomes. If you just pick a term, if you just call them all events, that's fine. Whereas an outcome is, or an event is made up of multiple outcomes, that's not for us to worry about, right? So just kind of pick one, but I'm being proper here. So 2 events or outcomes are independent if knowing the outcome of one does not affect the probability of the other. Okay, and so I'll highlight this. Okay. So flipping a coin, rolling a die, right? We kind of we get caught up in, oh well, I've flipped heads like 15 times in a row, so the next one has to be tails. Well, not really, because it has the same probability regardless of how many heads you've already flipped, right? The next probability of heads stays the same. It doesn't care, right? And so those would be independent events. Oh, and I totally have a funny somewhere where, let me see if I can find it. It's so important. It's not, but it's kind of funny. Ah, getting there. Ha. Copy. Steal it in here. Make it a little bit smaller though. There. Right. So here, third time's the charm, false. Each time has an equal probability of being the charm. So that would be independent events. That's not necessarily the case, right? But if you have independent events, then it is. Okay. So on the flip side, two events are not independent if knowing the results of one affects the probability of the other. So if you know that stocks went up yesterday, then they're more likely to go up today than to go down, that kind of thing, because they usually have this trend. Yeah, and eventually they start to go down, but that's, in the short run, you can tell when that's about to happen. Same thing with weather and disease. So if you have been in contact with someone who has COVID, then you're more likely to have COVID, right? And so the probability of you having COVID is higher, right? And so we understand these concepts of independent versus not independent events. One thing that trips people up is the disjoint versus independent events. So disjoint means they can never happen at the same time, versus independent means that, yeah, they can happen one after the other, but it has to do with the probabilities. So here I want to make a note on disjoint versus independent, only because it throws people off. So disjoint is when two events can't happen at the same time. Or no shared outcomes, right? No shared outcomes. So it has to do with the outcomes. Whereas independent is hinging on the probability. So the probability of one doesn't affect the probability of the other. So probability is not affected by a previous outcome. Okay, so the difference is one is talking about the outcomes being disjoint versus the probability of being of happening, or the probability being affected. Okay. So if A and B are independent, then the probability of A and B will equal the probability of A times the probability of B. Now, what I don't like about introducing this first is that people really latch onto it and say, okay, well, if I need to find the probability of A and B, then I can just do this. I can just multiply the probability of A times the probability of B. And that's not the case. That's only if they're independent. Okay, and so for that reason, it's at the bottom here of our formula sheet, but we introduce it now because we're gonna need it and we're gonna build on it, so it gets a little bit hairy here, but if A and B are independent, then the probability of A and B is the probability of A times the probability of B. But we know that a lot of the time, things are not independent. Okay, I think the example we're going to see involves, if you get an A on the midterm, what's the probability of getting an A on the final, right? We understand that if you got an A on the midterm, you're more likely to get an A on the final, right? Than someone who did not get an A on the midterm to get an A on the final, right? And so those would be non-independent events, and then this formula would not apply, right? So let me grab let me see. I'll just grab this again. Why not? So this is only if A and B are independent. Okay. We can use this property to determine if A and B are independent, right? Because if we have the probability of A and B, and we have the probability of A and we have the probability of B, then we can do this multiplication and we can just check to see if they are independent or not, right? Whether they equal each other or not. We have to be really picky about, okay, well, it has to be exactly equal, right? And so must be exactly equal in order to be considered independent. So I think I have an example. With a cute little image, but I'll leave her out of it. So let's see here. Maybe I'll do this. I'll crop top this. Oop. Okay. So in a math class of 30 students, 17 are boys and 13 are girls. So this gives us the probability of, so if we randomly select a student, what's the probability of picking a boy? What's the probability of picking a girl? And then we're told that on a unit test, 4 boys and 5 girls made an A grade. And I clearly stole this from some textbook sometime long ago, because that's weird wording, but whatever. If a student is chosen at random from the class, what's the probability of choosing a girl or choosing an A student? Okay. So what we can do is we can say, okay, well, I can show this with a Venn diagram. And this takes practice, right? Figuring out that you can show it as a Venn diagram. And so what I'm going to do is I'm going to say, okay, well, either we're talking about a girl or it's a boy, right? So the complement of a girl would be picking a boy. And then either they're an A student or they're not, right? And so let's see here. We can visualize the events using a Venn diagram. You don't have to, right? Because what we could do here is we could say, okay, choosing a girl, well, I know there's 13 out of 30 girls, so then I could just say it's 13 out of 30. That's fine. So we already know the probabilities, but for later on, it's just nicer if we're able to visualize all these outcomes, because then we can solve kind of more complex problems. How am I going to denote this? If I let G be a girl, so the event G denotes picking a girl, right? Or randomly selecting a girl. And if I let A be an A student, right? So usually if I'm using this shorthand notation, what we should do is we should define it somewhere, right? Otherwise, it doesn't really make sense to use that shorthand notation. But now what I can say is the probability of picking a girl. And I guess what I should say here is instead of just girl, I should say picking a girl and picking an A student. Sure. Picking an A student. So then choosing an A student, well, the probability of that is the same as the probability of A, right? Because A is picking an A student, it's shorthand for picking an A student. And what we see is that, okay, if we don't care what gender they are, then an A student, there were 4 boys and 5 girls, so a total of 9 out of 30 in the class who got an A. So 9 out of 30. You can convert these fractions into decimals. I know personally I prefer to work with decimals, but for this example, I'm going to keep working with fractions because maybe we need to brush up on fractions. And it's always good to keep the exact form. So I'll try to keep fractions as much as I can here. Okay. So we can visualize these events. So we already have the answers. That's fine. But it might be nice to just kind of visualize what's going on here. So that's what I want to do. So I've got kind of 2 things that I'm concerned with. So here, this rectangle denotes the entire class, right? That's my sample space. So S is the entire class. Okay. And then I'm going to have some of that class are girls, right? And so then everything that's not in this G circle, well, those would be all the boys, right? So I know that there are 13 girls and 17 boys. So the area outside the G circle is 17. And this throws people off too, right? Because we feel like we're given a lot of information, right? 17 boys and 13 girls, and then A students and not A students. And we feel like we need to incorporate all of that information when we actually only need to focus on one of the 2 options, right? We want to focus on the girls because that seems to be what the questions are about. And we want to focus on the A students, right? And so here, we need that overlap because there are girls who got A's, but there's also a circle that are in only the boys section. And so those would be all the boys that got A's, right? And so here we've summarized all the information. Now, it gets a little bit tricky because we have this overlap, right? Those are all the girls who got an A. And so what I'm going to do is I'm just going to put the raw counts in here. You can put, 5 out of 30, but I find that it takes up too much space. And so here, I'm going to show this, and I'm going to put 5, right? And this is the G and A, or G and A, put in brackets here. But how I remember is the cap, right? If you just draw a line through, it looks like an A, and so that's what makes it and, right? That's how I remember it. Okay, let's see here. So if there are 13 girls, then this entire circle of girls has 13, but we've already accounted for 5 of those, right? And so we've already considered 5 of them. So 13 minus 5, oh my gosh, is it 8 or no? I don't know. 13 minus 5, it is 8. Phew. So then what I have here in this kind of, maybe I'll use a different color. Let's use like a slightly different color. So here I have 8. Right? So the total G circle still has 13, but we've split them out as if they're A students or not A students. And then for the boys that are A students, right, we know that, okay, well, 5 of the A students have already been accounted for. Those were girls. And then we have 4 boys that were A students. So I'm going to put that here. And sometimes I call these like half moons, right? They're kind of the semicircle-ish of the Venn diagram. Okay, so then how many are left over? What's the remainder of the sample space? Those are the 17 boys that didn't get A's, right? And so here I have, let's see here, 17 minus 4, what's that, 13? Yeah. So then I have 13 boys who did not get A's, right? So they're boys because they're outside the G circle, and they didn't get A's because they're also outside the A circle, right? And then if we add these all up, so 8 plus 5 plus 4 plus 13, we should get a total of 30, right? So 8 plus 5 plus 4 plus 13 puts us at 30, and that is the entire class. So it's our entire sample space. Okay, let's see if we can answer some more of these questions. And like I said, you don't need the Venn diagram to answer these questions. Sometimes, you can figure out the questions just by looking at the values that are given, but sometimes I find the Venn diagram makes it a lot easier. So now if we want to know the probability of choosing a girl who got an A on the test, we know that there were 5 girls who got an A on the test, right? So 5 out of 30. Oops, I'm wrong there. So how do we denote it? The probability of choosing a girl who got an A, so a girl and an A, which is the probability of G and A, the intersection. That's 5 out of 30. And I'll keep it as a fraction just because I think it's irrational. So I'm just going to keep it as a fraction for the most exact value. What if we want to know what's the probability of choosing a girl or an A student? Now, at this point, the hardest part is reading this question and figuring out what I need to solve for, right? The values are all there. We've laid it out. We know the formulas, but sometimes it's really difficult to read the question and understand what you need to do. So in this case, I'm going to write this out as the probability of choosing a girl or an A, which is the same thing as probability of girl union A. Now, if we remember our formula, right, we know in general, as soon as I have this or here, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Oh, I got scrunched up there. Maybe I'll shove it over a bit. minus the probability of A and B. Okay. So now what I need to do, and it gets confusing, right? Because I have an A here, but that's not the same as this general A. This A is a placeholder. So wherever I see an A in the general formula, I want to map it to a G, right? And so what I want to do is I want to write this out as the probability of G or A is the probability of G plus the probability of A, right? Because wherever I see a B in the general formula, I'm going to write A. That's confusing, right? And the reason that I'm not swapping these around is because sometimes the order matters. So I want you to be in the habit of just being able to map these to the general formula and then just write them out. Minus the probability of G and A. I have all these components, right? We just established what the probability of G and A is, and we already saw what the probability of G was and the probability of A was. And that's going to happen a lot, right? For all these questions, I kind of take you by the hand and walk you through. So each of the parts builds on the next part. So if you catch yourself thinking, oh, I have to do all this work, that's probably not the case. Maybe sometimes, but for an assignment or something, but on a test, no. Usually I'll walk you through it just like this, and you'll have all the components that you can just use, right? And so try not to get tripped up there. Okay, so the probability of G, if we go back, was 13 out of 30, and the probability of A was 9 over 30. So we have 13 over 30 plus 9 over 30 minus, and this is why I kept all the fractions, the probability of G and A was 5 over 30. And what's nice, if we remember about fractions, right, to add and subtract fractions, I need to have a common denominator, which I do, which is 30. So now I can just add and subtract across. So if I go 13 plus 9 minus 5, that puts me at 17 over 30. So I'll show what I did here. 13 plus 9 minus 5 over 30, which is, if you wanted to skip to just 17 over 30, that's fine. Okay. So now I know the probability of choosing a girl or an A student is 17 over 30. Right? And that incorporates all the girls, but also all the A students who are boys. Right? We could have found this value just using the Venn diagram, right? I personally prefer to use just the formulas, but we can use the Venn diagram, right? If we go back here, so we want the probability of choosing a girl, right? Which is 8 and 5, right? But also it can be an A student, which is also going to keep this 4. So 8 plus 5 plus 4 puts me at 17 again. So that's the exact same answer. So you can get there using the Venn diagram, or you can get there using the formulas. Okay. We could also find this using the Venn diagram. Right, 8 plus 5 plus 4 over 30 is 17 over 30. Okay. Same answer, obviously. Just a different way of finding it. And to me, it doesn't matter how you find it, right? If you prefer the formulas or if you prefer the Venn diagram, but I've shown you both ways, and you just need to pick the one that you like. Or sometimes it's nice to confirm your answers using the other method, right? So just kind of have a way to check your answers. And finally, whoops. are choosing a girl and choosing an A student independent, right? Are these independent events? So now we have the probability of choosing a girl, we have the probability of choosing an A student, and we also have the probability of choosing a girl who is an A student. And so now I can use those components and I can check to see if they're independent, right? Using that formula that we had. In fact, I'm going to bump this down to a fresh page here. Okay, so if we want to see if they're independent, right, we want to check if the probability of A and B is equal to the probability of A times the probability of B, right? And I'm going to put a little question mark up top there. That's only true if they are independent. Okay. So for us, what that translates to is the probability of G and A. Does it equal the probability of G times, times the probability of A? So what we want to know is whether probability of G and A was 5/30. So let's do 5/30 here. Does it equal the probability of G, which was, oh shoot, I know I can't remember, 13/30 times 9/30. And if I do 13 times 9, puts me at 117, and then divided by 30 times 30, because my fun calculator reduces it. But I've got, this is 13/100 once it's reduced. Does that equal 5/30? Right? Doesn't look like it, but I'm going to convert to decimals just in case, just to check it out. So 5/30, 5 divided by 30 is 0.1666 repeating. And I want to know, is that equal to 13 divided by 100, which is 0.13? No, it's not. So since these two values are not equal to each other, then we know that these two events are not independent. What does that mean? It means that knowing that you picked a girl is going to affect the probability of it, of that person that you picked being an A student. Right? And from the numbers, it looks like the probability was higher that you would have picked an A student. But all we can say right here is that they are not independent. So since the probability of G and A does not equal the probability of G times the probability of A, we conclude that picking a girl is not independent of picking an A student. Okay. Therefore, right, just to kind of reiterate, but in a different way. Oh, and hopefully you guys are okay with the therefore notation. It's just 3 dots. So therefore, knowing that you have picked a girl affects the probability of that person that you've picked or the student that you've picked being an A student. So knowing that you picked a girl affects the probability that the student you picked is an A student. Get I think that was, why not? I'll bring in this cute little image. Why not? Whee! She looks so happy. She's an A student. That's us. Maybe not me. No. Mostly A's. Always a C+ in gym though. Okay, so the next section that I want to talk about is on conditional probability. So conditional probability is, let's see here. Is if we have kind of consecutive events, or if we think about, you write the midterm and then you write the final, that kind of situation, or in this example, right, you're going to have a group of high school students and some of their parents have a college degree and some of their parents don't, right, or at least one parent with a college degree. And then what's the probability that that person goes to college? So one thing has already happened, right? And then we're looking at the conditional probability of the next event happening. So usually we're talking about consecutive events. And how we visualize conditional probabilities are often in contingency tables, which we've seen in chapter 2, right? For categorical data, we said, okay, well, we can summarize it with a contingency table. And so in this example, we consider a sample of 792 teens, right? Where college means, which we've denoted by a C, means that the teen went to college immediately after high school. So it's not just in general they went to high school. We have these very kind of strict definitions of, okay, when would you be classified as going to college? Well, you had to go immediately after high school. And then the degree variable indicates whether at least one parent of the teenager completed a college degree. So do you have at least one parent at home who has a college degree? So we're going to use this notation here. So D is at least one parent has a college degree. And C is the teen went to college immediately after high school. So then we can talk about, okay, C or not C, so the complement of C, and D and not D, so the complement of D, right? And then we can talk about, okay, well, ignoring whether either of the parents has a degree, we can find just the overall number of students who went to college immediately after high school was 445 out of 792. Right. Same thing with the degree. So the total number of students who had a parent at home with, or at least one parent with a degree, was 280 out of 792. Right. And so we can read these values and we can pick out different probabilities just from this table. And so wording here can be really tricky because we just, even the slightest change in wording can make a difference. And I'll show you an example. So as our example, we're going to work through these 3 problems. Okay, so first thing we're going to talk about, and let's just read through the problems and just kind of try to figure out when we're going to talk about a conditional probability. I haven't introduced the formula yet, and we haven't, really talked about it, but it's when we're given some information and it's going to affect the probability. So it's kind of the step up from independent events. Why we talk about independent events first. So what proportion of teens have at least one parent with a college degree? So what we can do is we can just look at the table and we can find the proportion of teens. So remember, proportions or percentage or probability. What's the probability of randomly selecting a teen with at least one parent with a college degree? Well, that's going to be the same as this 280, right? But because we're not considering whether they went to college or not, right? So then we can look at the total of 231 and 49, which is 280 out of 792. So from the table, and maybe I'll crop this here. So from the table, we see that the proportion, which is the probability, so I'm still going to use that probability notation, the probability of D, right? So here, have at least one parent with a college degree. What is that? That's just, we're going to shorthand that to D. So what proportion of the teens are D, right? So the probability of D is going to be 280 divided by 792. We can use the exact form. I might just convert this to a decimal because it's kind of a messy fraction. So 280 divided by 792. I like to keep, around 4 decimal places at least, but also understand that when I round this value, so it's 0.3535353535 repeating. And so, sorry, I'll keep the exact equals 0.353535 repeating. When I round this, it becomes the approximate value. That's just to highlight to myself that, okay, I rounded this, and so that's going to affect my results. Whereas if I use the exact value throughout my calculations, I would get a slightly different value, right? So it just depends on what calculator you're using and kind of if you're able to store values or not. But sometimes, as long as you keep kind of 4 decimal places is usually safe enough. Okay. So here, using rounded values in our calculations, will yield slightly different results. Different results. But usually around 4 decimal places is safe. It depends on how many zeros you have, right? So if you have a lot of zeros after your decimal, then you should probably keep more, obviously, more information. But usually, but usually 4 decimal places is safe. Right, to kind of get you in that same ballpark. It'll make a difference, but not a huge difference. So usually I would recommend, at least 4 decimal places. I guess I should highlight the places. If you find yourself wanting to round. Okay. So now we have the probability of D, which is at least one parent with a college degree, gets really wordy. So then using that acronym or the D, the placeholder is really useful. Okay. Let me see if I'm missing anything here. No. I want to show you with just the table first. So we're going to answer these questions with just the table, just to show you that you can. And then I'll introduce the formula and just show you how it matches up. Okay. So given at least one parent completed a college degree, what's the probability that the teen went to college right after high school? So what I'm going to do is I'm going to snag this table here so that we can see it. Oh, did I do all of it? Kind of blinked while I did it. So blink and you miss it. Okay. So what we're saying is that, okay, given, maybe I'll use a different color here. So this given here is what makes it a conditional probability. So this is what makes it conditional. So given at least one parent completed a college degree, so what that means is given D, so here, this is the same as given D, what's the probability of C? What is the probability of C? Right? But it has that conditional statement of, okay, if we're only considering those with in the D category, so that's going to be all of these guys, right? So here we had 280 students who have one parent, at least one parent with a college degree, right? So that's the 280. So now I'm only looking at those 280, right? Because I've already told you, okay, given that we know this information, then what's the probability that they went to college? And so that's going to be this 231, right? So how we're going to denote this is using some special notation. And so we use the probability of A given B in general. So in general, we write to mean the probability of A given B. So this vertical bar, we read it as given. So then what we're going to have is I'm going to look at this and say, okay, if I just had to answer this with just the table, then I would translate the question into this notation, right? And so what I want to find is I want to find the probability of C given D, right? And that's not easy to make that transition, right? So what I'm finding here is the probability of C given D, right? Which is the probability of C given D, which is what the question was asking us for. Right? So now what I can do is I can look here and I can say, okay, well, 231 of those with at least one parent at home with a college degree, the 280, right, satisfy that criteria. So then this is going to be 231 over 280. Okay. Now, so you can solve this problem, you can answer it just by using the table, and that's fine. But if we wanted to apply the formula, then from the formula sheet here, oh, why would it want me to write it now? No. From the formula sheet, we have this probability of A given B is going to be the probability of A and B over the probability of B. So besides kind of reading this, we have to get familiar with the notation, but notice how the B here, I just kind of remember that, okay, the given part is what I'm dividing by later. And then in the numerator, I just have A and B. Okay, so, and of course you can have this written down somewhere and you can just rely on that. But also don't be scared, because you can just look at the table and figure it out from there, right? And so you don't need this formula necessarily, but it does help for trickier questions. So the probability of A given B, right, in general, now what I want to do is I want to map this to C given D, right? So wherever I see an A, I'm going to replace it with a C, and wherever I see a B, I'm going to replace it with a D. Oh, okay, so here, this is going to become, so the probability of C given D is the probability of C and D divided by the probability of D. And just to keep it on the same page here, I'm going to write across the page. I don't like doing that, but I just want to keep it all on the same page. So the probability of C and D is 231 over 792, right? So this is going to be 231 over 792. And maybe I need more space than what I'm giving myself. Okay, fine. That's how much I don't like writing across the page. Here we go. 231 over 792 divided by the probability of D, we already decided was 280 over 792, right? Just to show you what happens, I'm not going to use the decimal version because I'm going to cancel that 792. So I get 280 divided by 792. Remember, if I'm doing a fraction divided by a fraction, I have to flip and multiply, right? And so what I get here, is 231 over 792 times 792 divided by 280, which is going to cancel those 792s. And then I'm left with the exact same value that we found earlier, 231 over 280. Right, and that's exactly what we found here using the table. Right, and so here, notice this is the same value we found by just using the table. So for our purposes, you can use either or, but it's nice to see the matchup. Right? Okay, and I think I didn't copy. I ditched it. Whoops. So for the next example, now our job is to read this question, and the easiest thing will be if we can convert this to the notation that we're familiar with, right? And then we can kind of do a mashup of the formula and just using the tables, right? So here, given that a teen is randomly selected and she did not attend college right after high school, so that puts her in what category? And maybe I can grab that table again. Use the one that's not written on. So given that we picked someone, and so we know they did not go to college right after high school, right? And so we're focusing on this group of 347. So we know we're zeroed in on that group, okay? What's the probability that at least one of the parents has a college degree? So now we're looking at 49 over 347, right? That's easy for me to say because I know how to read these, but that's hard, right? That's going to take practice. And so how can I kind of formulate this? So I'm going to rely on the formula. And I'm going to say, okay, I'm going to need to convert this question into that formula. As soon as I see the word given, right, then I know that I've got this conditional probability. Okay, and so what we're trying to find is the probability of at least one parent. So what's the probability that at least one of the parents has a college degree? That's a D, right? And given that the person, the student you picked did not go to high school or did not go to college right after high school, that's the complement of C, right? But that's the given part. So that actually comes after. So what we're trying to find is the probability of D given not C. Okay. So if I remind myself of this formula here, copy, maybe make it a little bit smaller here, then I can map this out to match this formula. It's going to take some concentration, right? Especially in the beginning. But how I read these is it has to be the first component and the second component divided by just the second component. Okay, so it has to be the first and the second. So A and B divided by just the second. But you can write these all down and you can have them, but it helps if you have little tricks up your sleeve. So that's the probability of D and not C divided by the probability of not C, or the complement of C. Okay. So what we have, right, D and not C, that's these guys here, right? They had to have at least one parent with a college degree at home and not go to college immediately. So that's the 49. And the probability of that is 49 out of 792, right? So it's going to be 49 divided by 792 divided by not C, which is 347 over 792. And again, these fractions are going to kind of flip and multiply, right? Fraction over fraction, flip, multiply, and then the 792 goes away. So I get 49 over 792 times 792 over 347. And this cancels 792, 792. And I'm left with 49 out of 347, which you would have arrived at, right? Just if you read the question really carefully, but then it's nice to be able to back it up with the formula. I see that I'm all out of time. So we'll pick up here next day. And if you have any questions, let me know. Otherwise, I'll see you on Wednesday. Stop this
Thank
recording.
you.
Thank you.